This video is on the preparation of alcohols. Alcohols are often found in nature, i.e. they are a natural product that you can just extract. Because of this, they are a very common starting material. However, sometimes you might need an alcohol that is not available in nature, and therefore you're going to have to make it yourself. So what is the easiest way to make an alcohol? Well, it's an SN2 reaction with the hydroxide as a nucleophile. As pictured here, we see the hydroxide replacing the leaving group, and voila, we have an alcohol. So primary alkyl halides are a great starting point. They have a good leaving group, easy SN2 reaction. For example, with this benzyl chloride derivative, if we mix it with sodium hydroxide and DMF, we will end up with the benzyl alcohol derivative at relatively high yields. This reaction under these conditions yields a yield of 85%. Using a hydroxide as a nucleophile under SN2 conditions also works well with secondary alkyl halides as long as the SN2 conditions are favored, i.e. the electrophile is not too bulky and the solvent is aprotic. So for example, here we have this cyclopentenyl chloride reacting with sodium hydroxide and acetone. Once again, we get beautiful substitution with 88% yield. However, hydroxides are not used with unfavored secondary or tertiary halides, as this would lead to elimination instead. In this case, we must use a weaker nucleophile such as water. Of course, this is now going to follow the SN1 mechanism. As you'll remember though, there is a competing elimination reaction going on, and if we follow, for example, this reaction, we'll notice that the water will replace the tertiary chloride at only a 48% yield. The rest will probably be still elimination. Just as an aside, a reaction where the solvent is also the nucleophile is referred to as solvolysis, whilst when it's with water, like in this case here, it is a hydrolysis reaction. Now you practice. What would the products be of these following reactions? You may pause now. And here are the answers. SN1 reactions are never ideal in a synthetic step because we end up with the mixture of products. So in other words, we're going to end up with a low yield. However, hydroxide, as we said, gives poor yields too because we get elimination on secondary halides that are bulky. Pretty much the hydroxide is too basic, it's too reactive. We need to modify it to make it a weaker nucleophile. How could we do this? Well, theoretically speaking, if instead of a proton on the negatively charged oxygen, we had something that was electron withdrawing, it would probably be a weaker nucleophile. Well, do we have any examples like that? Say something that can give resonance to that oxygen negative charge? Well, yes, the carbonyl. The acetate anion is a weak base and a weak nucleophile. Therefore, it really does not favor elimination. This means that we can safely do a SN2 reaction on a secondary alkyl halide without worrying about causing any elimination. Of course, you end up with an ester and inversion of stereochemistry if there happens to be any, just like in this example, at a very high yield. Luckily for us, there is a hydrolysis of an ester that will yield us the alcohol. Now this is not SN2 chemistry, so don't worry about it. We will cover it more in detail in organic too. But doesn't mean we can't abuse the method now that we're aware of it. So for example, in this reaction here with 3-chlorohexane, we can make the 3-hexanol under these conditions with inversion of stereochemistry, of course. Now you try with this molecule. You may pause now. And here's the answer.